Thank you, college. Thank you, Michael, give me the opportunity to share my research with the college and also with alumni and in such a big audience. And okay, so first about myself, I 2008, after I graduated from MIT, and then I spent 3 years with the GE Global Research Center as a mechanical engineer to help to analyze the aircraft engines, the bird impact safety, and also the wind turbine designs. So this is I spent about 3 years there. And after that, I joined UCF in 2011. And from to now it's almost 10 years. It's unbelievable, so fast. And I teach several courses at our college, 3 undergraduate courses and in mechanics and machine design, and also the graduate level, most of graduate level courses, and all in solid mechanics or computational mechanics. And so, and my research interest is still centrally on mechanics, constitutive modelings of the material plasticity and fracture for different materials, and lightweight design in vehicle industries. And recently is on the like I battery, the car battery impact, and also the soft tissue mechanics. Okay. The first is about one main research is the lightweight design in automotive industries. So we know that transportation industries account 27% of greenhouse gas emission. So that's why car industries and also aerospace industries, they have the push to adopt lightweight materials which can achieve the more energy efficient design. And you can see the picture on the right. You can see that there's a goal from Department of Energy try to achieve the 54.5 mpg microgallon efficiency in until 2025. I don't know, probably this is still a little bit not reached the goal yet, but we can see over the year they push the limits. And so they set up with the goal is that four materials. In the short term, they're going to using advanced high-strength steels and aluminum alloy. And in the long term, they're going to adapt, let's say, magnesium alloys and also polymer matrix, carbon fiber composite and car bodies. So every year, right? Car industry is different with others. Every year they need to have new model. No matter it's the small innovation, small change or big change. Every year they have to do so, because otherwise the competition is so keen. So that's why they adopt the new materials. But material is not just you have to, it's light or it's high strength you're going to have. Usually it's a trade-off. When you increase the strength, you're going to decrease the ductility. You're going to see fracture here and there. So this is one example here is the left-hand side is the magnesium, the trunk lead, right? So it's unbelievable. Magnesium is only 25% the density of steel. So if you can use there's a magnesium car body, you get the car body weight can be only 25% of that. But it's very difficult to two things. One is oftentimes you see fracture, and during the stamping, during the impact, and then you sacrifice the safety feature of that. And the other one is the cost, right? The cost is also very sensitive. So this is the reason. And we have been focused on this research for 10 to 20 years. And we started with aluminum alloy, and we have to get a better model, not just in the material science division. Usually they just test one or two, one tension, one compression, and it gets some rough ideas. But in the mechanical design, we need something more accurate. So that's why we test as many loading conditions we have, and then put the fracture locus. When they're going to fracture, usually material is easy fracture in tension. In compression, you don't see much fracture. And we test all of them and then input it into the commercial code for simulation. So that's why for bulk materials and for metal sheet, this is magnesium. And recently, we expand the research to additive manufacturing, right? So this is another emerging technology, and we collaborate with Dr. Yong-Ho Song and Dr. Da-Zhong Wu in our college, and they print metallic materials, or maybe design this microlattice structure, which can, during the impact loading, they can absorb as much energy and while and, have a lightweight features. So if you put it in the graph, yeah, this is kind of outstanding, right? So this is a research we are try to push to the limit, so to have an outstanding outcome, and then for the future design. Okay, so this is the mainstream of that. And second part of that, my research is centrally focused on mechanics, right? So this is another one of the mechanics of soft tissues, and it's really timing that our first presenter today is from College of Medicine, Dr. Parks, and give ideas about research in our College of Medicine. And this is when I like to expand my research to also to soft materials, not just metallic materials, hard materials, right, but also soft materials. And we have been this collaboration with Army Research Lab in IST for 5 years, and also Dr. Kasaf in our MAE department, and Dr. William DeCampoli is from College of Medicine, and they give us material samples on pigment tissues. So we try to understand that the tissue mechanics. Tissue is very complicated. So two things. One is it's highly nonlinear. So you're going to see that, right? All the stress strain curve is nonlinear, and also go to very, very large strain, right? 500%, 800%, is really large, and also highly anisotropy. So it's very, very complicated. We test hundreds of tests for that. We get the material samples from them, and also we try to characterize and what kind of material is suitable for the military medical simulation and training purpose. So we identify material which can be used in Army Research Lab. They can identify what kind of candidate synthetic tissues is best match the human being one, or maybe the training purpose one. So we designed those kind of groups, 3 printed part, and run the punch simulation. Try to simulate the procedure, the needle punching through tissues, or maybe scissors punching through that, and also those kind of it's much closer as possible to the real ones. And of course, within the have the all flexibility, low cost, and so on. So and in the future, I'm going to look into more into tissue fracture. We do a lot of the metallic material metals fracture for, this has been researched for 100 years, but the tissue fracture is relatively new. So this can be, this area can go to big in the future. So this is the second part. And third one is our recent research more going to the manufacturing. Right. So I explained research not only on mechanics, but also manufacturing on energy efficient the nano composites. So usually in mechanics, people try to increase the material strength and reduce the density. Also do the trade-off between material ductility and strength. But another research is kind of less is on how to improve the conductivity, right? The thermal conductivity and also electrical conductivity. And so in this, the fund from DOE, we used our idea to encapsulate the CNT and then put in a powder compaction and then do wire extrusion, and then we can increase wire. We can comprehensively increase, not only increase the strength, but also increase the thermal and electrical conductivity. Electrical is a little bit difficult, but thermal certainly shows very good. And we also try to build some computational analysis, try to understand what's the mechanism, right? In how much increased, and what kind of interface property we can better improve, comprehensively improve, right? Mechanical strengths and conductivities. But certainly it's a trade-off. While you increase the material strengths, and then you're going to decrease ductility. So that's why when to the metal forming, we have to do wire extrusion, and also needs to go to higher temperature. Right? Those manufacturing processes have to do elevated temperature, and we spend it has been 2 years efforts on these subjects, and some results are good. For example, our vibration assist the powder compaction. You can see this one. We increase the less porosity of the material, and the quality is getting better. So we're going to this year we're going to continue on that. And in terms of the near-term and short-term plans, the near-term, we're going to continue to manufacturing on the nano composites, which can achieve the good quality, right? So we can produce the copper and CNT wire, aluminum CNT wire with good quality. This is continual research on that, and also the energy absorption, the additive manufacturing technology used to produce the better alloys and also better microlattice can achieve the outstanding energy absorption rate. Of course, normalized by density, right? Maybe also normalized by the cost. Right? But this is certainly, this is very interesting. We have published several good papers on it. And for the traditional research with a lot of the collaboration the past few years with the car industries and also aluminum and steel industries, we want to push to the high strain rate in high temperature to understand the material plastic formation and fracture at high strain rate and high temperature. This is the near term in 1 to 2 years, of course, maybe 2 to 3 years. And in the long term, I like to still stick with this, understand the fundamental mechanisms. For example, microvoid growth, and we have thousands of specimens in my lab. So we have to see what's the fundamental mechanism, and also at the multi scale how those fractures occur. So this is long term, and if we if we focus on that, we can have a larger impact. And the second one is on the safety of the battery pack, the car battery, electrical vehicles, and looks like this is the area is going up very, very fast. So we like to, this is also composites. Initially research more on the metallics, now with more and more to composites. And actually the car batteries is composite. You can see the structure here. So we're going to, go into the battery pack, and it's not only battery pack, but also the fundamental level, how the, this is different scale, in the micro scale, in the nano scale, and also in the big scales. So it's very, very challenging. And the long-term plan number 3 is to, I'm trying to set up in the long term and has the center level, and you can see that the Cater is very successful in our college, and also 2 weeks ago the president gave the talk to our college in how to increase the visibility, the impact of college is to center level. And also recently the MA department has have a new faculty, I think 5 or to 10, right? Except 5 new ones, very, very good in mechanics. So now is the time we can group together, becoming the center level research, and we are very comprehensive on testing, modeling, simulation side. We can thinking of large proposal together in the center level, which can increase our visibility and reputation for sure. And of course, the last slide is acknowledgement. So and of course, it's our funding agencies and also the many collaborators at UCF and Dr. Evan Abradi from Korea, Lian An, Kwang Fan Chen, and Dr. Kasab, Dr. Song, Dr. Wu, and of course Yang Yang, right? Yang is from the material science and department, or probably on the battery side, and also my graduate students, right? Certainly they do all the work. I just guide them. They write a paper and then they do the work, and so of course. PhD students, master students, of course, a lot of the undergraduate students. Like my lab has some students. We have a large student pool for the undergraduate students, and they get experience there. And some stay for long, like senior year, junior year, master, and PhD. Okay. So this is the end of my talk, and thank you very much.